Okay, so before I get into kind of the implications of what this means, let's just look at an example. Okay, so we want to find the work done by this gravitational field, and we've already looked at it a little bit, moving from these 2 points, from the point 3, 4, moving from the point 3, 4, 2 to the point 2, 2, 0. Okay? So the first thing we need to do is we need to make sure we can use the fundamental theorem. Because notice that the fundamental theorem for line integrals, if we go back, notice it has to do with the gradient. It's the gradient of some three-dimensional function x. Okay, so we want to use some gradient field, and here f isn't a gradient field per se just yet. F is actually a force field, and we can figure out what the gradient field is going to be. And we actually, I think we already looked at and here, this x represents a vector, so x kind of is, we'll say x, y, z. And I think we already looked at finding this function f, and it's going to work out to be the little mass times the big mass times that gravitational constant over the magnitude of that. So in other words, it just kind of varies with the inverse of the square root, or the inverse of the radius. So this kind of down here, this is just the radius of this point, the distance from this point to the origin, and so gravity just kind of varies with that. We've already seen that a little bit. Okay? And so what we can do then is, if we know that this big F of x just equals this gradient, then we know to find the work. Well, remember, work is defined as the integral over our curve from of f dotted with dr. Well, we know that big F, that force vector, or that force field F, is just equal to the gradient of this F here, dotted with dr. And now, we can just use the fundamental theorem, because we have the gradient of F dotted with dr over this curve. We know that this is exactly equal to F of our ending point, which was 220, minus F of our starting point, which was, I already forgot, maybe 3412. So this is just using the fundamental theorem for line integrals. And because remember, it says that if we're taking the line integral of a gradient vector field, all we really have to worry about is the endpoint. So all we have to do is worry about these endpoints here. Okay? So let's look at what f of 220 and f of 3412 are going to do. Okay? So f of 220 minus f of 3412 is going to be equal to little m times big M times g, all divided by the square root, 2 squared plus 2 squared plus 0 squared, minus little m times big M times g over the square root of 3 squared plus 4 squared plus 12 squared. And so if we factor out that MMG, we're just going to have 1 over the square root. 2 squared is 4, plus another 2 squared is 4. And so that's just going to be the square root of 8 minus 1 over the square root. 3 squared plus 4 squared is 5 squared. And 5 squared plus 12 squared is 13 squared. And so this is actually just going to end up being all over 13. And so I think we can leave it like that, or if we want to simplify a little more, we could bring it to m times g, 1 minus 1 over 2 squared root of 2. And so this would be the work done by that gravitational field. So that's kind of an example of putting that theory to use, that theorem. But let's kind of backtrack and take a look at some implications of this really pretty. I mean, it's obviously the fundamental theorem, so it's obviously very important. Okay. So if we have two smooth paths, C1 and C2, that end at a common terminal point, what does the theorem tell us? So we already know that in general, if we just have two vector fields and we're integrating along two different paths, we're going to get two different values. We've seen that already. Remember, we looked at kind of, if we think of maybe one path here just being, maybe this could be C1, and then C2 might come all the way out here. And so when we do this line integral, we already kind of saw we kind of know to expect that we're probably not going to get the exact same value. Because the line integral depends on path. And so we've already seen that. But what does this tell you? Is that always the case? Will they always be different? Because remember, the restriction on the fundamental theorem is that the vector field we're integrating over has to be the gradient of some function. And so if we're integrating over the gradient field of a continuous gradient del f here, so as long as this is continuous, then the integral along these two different paths is going to be equal. So as long as they have the same common end point and beginning point, then the integral is going to be equal. Okay, and so that's kind of a big deal, if you think about it. And so, remember, we defined a conservative vector field we just defined a conservative vector field as a vector field that is the gradient of some function. So this just means that this vector field is the gradient of some function in other words, if we're taking a line integral through a gradient vector field, then all we have to worry about, it only depends on the initial point and the terminal point. There's only two things we have to worry about. It's totally independent of path, and so we actually call that independent of path. So if a vector field is the gradient vector field of some function, then that vector field is independent of path. Okay? So all we're saying then is that if we can come up with two paths, notice it says any two paths. So it's true for any two pair of paths that go between 2 points, then we say that this vector field is independent of path. And we're going to kind of look at different ways we can show that something's independent of path, or maybe guarantee that perhaps, on the other hand, it is not independent of path. And so, if you know, we know that conservative vector fields are gradients of other functions, and the fundamental theorem tells us that if we take a line integral of the gradient of some function, it only depends on the endpoints. That means, that tells us absolutely that every conservative vector field is independent of path. And so that's really the big implication of the fundamental theorem, more than anything else. Conservative vector fields are independent of path. All we have to worry about are the endpoints. Okay? So we have to get through a couple very quick definitions, and then we can go through some examples and see exactly how we can put this fundamental theorem to use. Okay, so I want to briefly go through an example, or go through this definition of a closed path. So it says a closed path is a path whose terminal point coincides with its endpoint. What in the world does that mean? Well, all that means if we start here, then we're going to kind of go along some path, and then we're going to end right back there. So that's a closed path. That's our start point and our end point. Okay, so that's all a closed path is. We can kind of think of just like a loop, if nothing else. And so what this says is that if we integrate over every single closed path, so we're integrating this vector field F over every single closed path C, and they always equal 0, then it's going to be independent of path. Okay? And let's kind of look at why that is. It actually is pretty intuitive. Okay? So first of all, let's assume that F is independent of path. Okay, so when we assume it's independent of path, and we have some closed curve C, let's pick 2 points on C. I'm going to pick this to be A, and this to be B. And then what I'm going to do is I'm going to declare this half and A over to B, kind of going this way. I'm going to call that C1. And I'm going to call A going to be this way. I'm going to call this C2. Okay, so let's look at the integral of FDR over C. Okay, so we already kind of know that we can break this up based on the integral. Okay, so if we want to kind of think of maybe we're starting at A and we're going to try to go all the way around and come back to A. So what we have to do is we'd have to integrate along C1 and then notice to get from B to A going this way, now we're thinking of coming over here, so we're going this way. This is going to be negative C2. Okay, so we would integrate from along C1 of F, and then we would integrate in the negative direction of C2. Okay, but we're actually already done, because notice C1 and C2 have the same endpoints. And also notice, that F is independent of path, and so what that tells us is that the integral along C1 is equal to the integral along C2. And we know, because of, if we kind of go into reverse orientation, all we're going to do is pick up a negative. This is going to be equal to negative times the integral along negative C2 FDR. And so being that these two are opposites, they're negatives of each other, then that tells us that the integral over the whole thing, when we add those two up, that's going to be equal to the integral over C1 FDR minus the integral over C1 of FDR, because those are opposites, and so that's just going to be 0. And so that proves, when we want to go that direction, that if it's independent of path, then around any closed loop, we're going to get the integral to just be 0. Okay? And so to kind of go the other direction, we actually do almost the same thing. So now let's assume we want to assume that the line integral around any closed loop is just equal to 0. So we're assuming that that's true no matter what. Okay, so let's kind of, again, start like we did before and pick some arbitrary curve C. And we have, again, two arbitrary points, A and B. And so being that we're trying to show path independence, we want to show that no matter which way we get from A to B, we're going to get the same interval. Okay? And so again, let's kind of think of calling this one A to B this way. We'll call that C1. And now I'm going to go this way again from A to B, and we're going to call that C2. So we want to call that C2. And what we want to show is that the integral along C1 equals the integral along C2. Because being that this is an arbitrary closed circuit, a closed loop, we're not really picking specific ones. So if we can show that this is true in general, then that means that this is going to be path independent. Okay? So how can we show that? Well, what we do know is that the integral along C of f dr equals 0. Kind of based on our assumption. And so what we can do is we can think of breaking C up again. So we're breaking up our curve C. But notice now, we're going to go from A to B along C1, but then we have to take negative C2 to get all the way back to A. So C, in our case here, C equals C1 union negative C2. And so then the integral along C is just going to be the integral along C1 plus the integral along negative C2. And so being it's equal to 0, we can see that the integral along C1 of f dr equals negative integral along negative C2 of f dr. And so if we change that orientation here, if we go along positive C2, then we're going to get the opposite of that integral. So we're going to have positive f dot of dr, which gives us our result right here. And again, because all those were arbitrary, because we picked arbitrary closed curves and arbitrary points, that establishes the result kind of in general. And so what we're left with is